In this video, we continue our discussion of chemical kinetics. Now recall that we talked about chemical kinetics covering two things. It covers how reactions occur and how fast they occur. And right now we're focusing on how fast reactions occur. So we're taking a look at reaction rates. So when we talk about a rate is a change in some quantity over time. Now our units are going to vary depending on the quantity we are interested in. However, generally, reaction rates are defined as being the change in concentration over the change in time, where those brackets are indicating molar concentrations, or we talk about a change in pressure over time. So we might talk about pressure more if we're dealing with reactions of gases. Now, rates can be looked at in terms of the rate of disappearance of reactants or the rate of appearance of products. The rate of disappearance of reactants is referring to how fast the reactants are being consumed. The rate of appearance of products is referring to how quickly products are formed. So with that in mind, for a given reaction, we've got reactants being used, we've got products being formed. So we can talk about our rates in a variety of ways. So we're going to have to make sure we always specify what we are referring to. Rates are always expressed as positive values. So even though our reactants are going down, we're going to express that change as positive. We're going to look at it as just the given amount that's changing. Stoichiometric ratios in our balanced equations lead to different rates depending on what substance we focus on. So we're not going to generally talk about a single rate. We're talking about a rate in reference to a single reactant or a single product. And one substance to another in our balanced chemical equation, they are related through our mole ratios, just like you did when you looked at stoichiometry in your first semester course. So if we look at an example, we've got a reaction in which it was found that the rate of nitrogen formation is 0.52 molarity per second at a particular point in time. And that's for the following reaction, in which we've got ammonia, NH3, reacting with oxygen, producing nitrogen and water. So based on this information, we want to determine the rate of disappearance of NH3. And the information that we know from the problem is that we know our rates in terms of the formation of nitrogen. We also know that nitrogen and ammonia are related by the mole ratios in our balanced equation. Now looking at the concentration we have, that 0.52 molarity per second of nitrogen, what that means is that I have 0.52 moles of nitrogen being formed per liter per second. To figure out the rate for the ammonia, we can treat this as a conversion factor in which we are essentially converting moles of nitrogen to moles of ammonia. So we're starting off with that rate, the 0.52 moles of nitrogen per liter per second. And we want to convert to ammonia. So again, pulling back those tools from first semester chemistry, we're going to look at our mole ratios. My nitrogen has a coefficient of 2. My ammonia has a coefficient of 4. When we set up that conversion to convert moles to moles, we're going to set this up so that we cancel the nitrogen mole. So we're putting 2 moles of nitrogen on the bottom. We're putting 4 moles, the coefficient for the ammonia, on the top. So multiplying through, my moles of nitrogen cancel. I've got 0.52 times 4 divided by 2. That's going to give me 1 mole per liter per second for the ammonia. Or we can go ahead and simplify that. That's 1 molarity per second of my ammonia. So still working with this same example, next we want to determine the rate of appearance of water. So again, we know our rate in terms of formation of nitrogen. We also know that nitrogen and water are related by the mole ratio in our balanced chemical equation. We have 0.52 molarity per second for the nitrogen. So again, that means 0.52 moles of nitrogen per liter per second. Now we want to stick with using the number that we were given because we already are certain of that number. Now, we can treat this again as a conversion in which we convert moles of nitrogen to moles of water. So again, we're going to start by taking that rate, and we're going to multiply it by a conversion factor. If we look back at our balanced equation, we have 6 moles of water for every 2 moles of nitrogen. So we set this up with the 6 moles of water on the top, the 2 moles of nitrogen on the bottom. So the nitrogen moles cancel. And I end up with 1.6 moles per liter per second of the water, which is the same as 1.6 molarity per second for the water. So in both of these cases with our examples, we use conversion factors. And we're asked in problem 14, where are these conversion factors coming from? So where is this portion coming from? And we got those values from the coefficients in our balanced chemical equation. And so just like we did with stoichiometry, anytime we want to convert between moles of substances, we can use our coefficients. So then we're asked, why do we see different rates for nitrogen appearance and water appearance? So the nitrogen gets formed at a rate of 0.52 molarity per second, but the water is getting formed at a rate of 1.6 molarity per second. We're seeing that difference in rate because of the number of molecules that actually get formed according to that chemical equation. It's the result of having different mole ratios. So it's very common for a reaction that we might have one particular reactant or product that's easier to measure than the others. So then we measure its amount over time so that we can get that rate. And then we use that to relate it back to other components in our balanced chemical equation. Now looking at our next problem, we're asked to consider the following reaction. We've got 2N2O producing nitrogen and oxygen. We're told that in the first 75 seconds of this reaction, 0.136 moles of oxygen are produced in a reaction vessel with a volume of 0.5 liters. And we're asked for the average rate of oxygen formation during that time interval. So first of all, we've got to know we're looking for rate, and that rate is going to be equal to the change in concentration. So we're looking at the oxygen. We're looking at the change in the oxygen concentration over the change in time. Now I have time. We're talking about in the first 75 seconds. So if we're talking about the change in time, it's the final time minus the initial. So if we're talking about the entire first 75 seconds, the initial time would be a time of 0. Now, in order to finish calculating this rate, we need to know the oxygen concentration. And we can assume that the oxygen is starting at an initial concentration of 0 molar. Because we assume we don't have any product if we haven't started our reaction yet. So I need to know the concentration after 75 seconds. And so the concentration of my oxygen at that time is going to be the moles that are produced divided by the volume. So the 0.136 moles divided by my 0.5 liters gives me a concentration of 0.272 molar for my oxygen. So we plug that into our equation, and we're going to get that our rate is 0.00363 molarity per second in respect to the oxygen. So again, we've got to indicate our chemicals. We can't just say molarity per second, because what are we referring to? It's going to be different for different substances in our equation. So with part B, we're asked during the same time interval, what would be the average rate of disappearance of N2O? So based on the information we have the rate for the oxygen. That oxygen rate of 0.00363, that's how many moles of oxygen we produce per 1 liter per second. And we're going to convert the moles of oxygen to moles of the dinitrogen monoxide, the N2O. We need to cancel the oxygen. Its coefficient is 1, so on the bottom we've got 1 mole of oxygen. The N2O's coefficient is 2, so on top we have 2 moles of N2O, which is going to give me 0.00725 molarity per second, and this is in terms of my N2O. So to summarize, whenever we talk about rates, we are talking about a change in some amount, typically concentration or pressure, over time. It's different for different substances within my balanced equation. And so how fast my products are forming may be different than how fast my reactants are being used, and that's dependent on the coefficients in my balanced equation. And so we cite reaction rates for individual substances, and they are related to others through those coefficients.